So this example is similar situation. We have the same open top box from the previous example. So let's just copy it down again. It's got a square base. My square base doesn't look very square, but just pretend with me. All right, so same base, same volume, 216 inches cubed, which again, just like before, means that y is equal to 216 over x squared. And this time, we're looking at building this box. The cost of the material is, for the base, is 20 cents per inch squared. And the cost of the material for the sides is 30 cents per inch squared. And we're trying to minimize the cost now. Okay. Well, the cost is just going to be the cost of the base plus 4 times the cost of one panel. Well, the cost of the base is the area of the base times its cost, 20 cents. Let's have cost in dollars. The 20 cents is $0.2 plus 4 times the area of the side times the cost of the side, 30 cents. So it becomes almost the exact same problem, just with a slightly different objective function. So our cost, 0.2x squared plus 1.2xy. Just like before, we'll substitute that y in to get a cost function as a single variable. Y is 216 over x squared. We have the same domain as before, x just being positive. We don't have any constraints on our money, apparently. We just want to do it as cheap as possible. So I'll finish through this problem real quickly. Should have recommended that you just do this on your own and see if we get the same thing. Let's simplify the cost function. 1.2 times 216. I'm not doing that in my head. 1.2 times 216 is 259.2. Then we want to take the derivative of this, set it equal to 0, just like before. Because really this is just a scaling of the surface area. As x goes to infinity, we have to check both endpoints. And just as before, look at this function, look at this cost function. As x goes to infinity, the cost goes to infinity. As x goes to 0 from the right, the surface area went to infinity. Well, the cost is also going to go to infinity because the cost is just a scaling of the surface area. Well, a linear combination of different parts of the surface area, but the point still stands. So just like before, we have a minimum. We don't have a maximum. There's no maximum cost. We could have this cost as much as we wanted. So we take the derivative of the cost function, and we're going to eventually set it equal to 0, because again, this becomes very, very similar to the last problem. To set this equal to 0, because again, we don't have to worry about when it's undefined, because when it's undefined is outside of our domain. We'll multiply both sides by the LCD, which is x squared. That's going to give us 0.4x cubed minus 259.2, or 0.4x cubed equals 259.2. Divide both sides by 0.4. That's the same as multiplying by 5 halves. 259.2 divided by 0.4 is 648. So x is about the cubed root of 648. Cubed root is the same as an exponent of 1/3, 8.653 inches. Just like before, y is going to be 216 divided by x squared. So y is going to be 216 divided by this. Another way of doing a shortcut is writing it like this. Squaring it is just an exponent of 2/3 instead of 1/3, and dividing is multiplying by a negative exponent, 2.884 inches. Slightly different dimensions. This just wanted us to write the function. But yeah, to minimize the cost is when the box is 8.653 inches by 2.884. So a pretty short box, honestly. It's because the cost of the sides is more expensive. And we're trying to minimize surface area. So having a lot on the base is also good because there's no top. And the min cost, if we wanted to, you could plug that into your cost function. Didn't ask us to do this, but it is kind of interesting. If we plug that into our cost function, we get, oh, I didn't put our cost function. Our cost function was 0.2 x squared plus 259.2 over x. So when x is 8.653, the cost is about $44.93. All right, that's how you approach these problems. Let me know if you have questions, and good luck. I just do a bunch more problems in the next video too. There's tons of videos here, but just lots of good review for you, hopefully, as you need them if you want to see some more different kinds of problems.